Hi everyone. I want to start this video by talking about the ideal gas equation. In the last video, I taught you the three different laws, Boyle's, Charles, and Avogadro's. And I briefly mentioned that when you combine all of those three laws or expressions, you can form a single master equation, which is the ideal gas equation, PV equals nRT. And this ideal gas equation basically describes the relationship among the four variables that we dealt with: pressure, volume, temperature, and moles. Let's talk about an ideal gas for a minute. Ideal gas is exactly what the word says. It's ideal, okay? So it's hypothetical. It's not a real gas, all right? But it's a hypothetical gas whose pressure, volume, and temperature can be completely accounted for by this equation. Now, even though in nature there really isn't such a thing as an ideal gas, the ideal gas approximation works really well, for most reasonable temperature and pressure ranges. So it basically can be safely used to solve a lot of different real gas problems. But before we apply this equation, I want to talk about the gas constant that it has in it. Now, at standard temperature and pressure, which is 0 degrees Celsius and 1 atm of pressure, many real gases behave like an ideal gas. So that's another reason why we're able to use this ideal gas equation. Experiments show that under these conditions, 0 degrees Celsius and 1 atm pressure, 1 mole of an ideal gas will occupy 22.414 liters, which is sort of close to what the volume of a basketball is. What's important here is that when you deal with the ideal gas equation, we must remember that we're dealing with certain units, okay? So we're going to deal with ATMs, liters, moles over K, all right? So of course the ATM is the pressure, the liter will be your volume, and your number of moles, of course, is the N, and T is in Kelvin. Always Kelvin, never Celsius. So standard temperature and pressure is at 0 degrees Celsius, but that means it converts to 273 Kelvin. Now, the value for R, which is the gas constant, is 0.082057 liter ATM mole K. You don't need to memorize this. I will give it to you in an exam. But it's important that you understand how they arrive at that number. Basically, what you would do is you would take 22.414 divided by 273, and the number you should get is 0.0821, so on and so forth. But with those units, liter ATM over mole K. And that's why it is that number, because at 1 ATM and 0 degrees Celsius, 1 mole of gas will occupy around 22.4 liters. The ideal gas equation is great because if we know 3 of the variables, then we can calculate the other one by using the ideal gas equation. One thing I want to point out is unless they tell you, you have to assume that the temperatures that they give you in these problems are exact. So you wouldn't use them in calculating the number of significant figures. So keep that in mind when you do these ideal gas equation problems. Let's do 2 of them right here. Calculate the volume in liters occupied by 2.12 moles of nitric oxide at 6.54 atm and 76 degrees Celsius. This is a plug and chug. So basically, I would solve what they're looking for is volume. So I start with PV equals nRT, and then I obviously would solve for volume. That would make it V is equal to nRT over P. And then I just plug everybody in. The only thing you have to make sure is that you have the units that you're supposed to have for the ideal gas equation. And everything they give you works except for the temperature. You cannot use Celsius in the ideal gas equation. You must use kelvins. So we would put 2.12 moles times 0.802057 liter ATM over mole K times the temperature, which is 76 degrees Celsius, but you got to convert it to Kelvin, so it ends up being 349.15 Kelvin. And then all of that divided by 6.54 ATM. You notice that the R, the gas constant, helps you cancel out every single one of those units except the one that you need. So you end up with 9.29 liters. Okay, let's do another one that takes a little bit more knowledge. So this one says, what is the volume in liters occupied by 49.8 grams of HCl at STP? We know that STP means standard temperature and pressure, which is defined as 0 degrees Celsius and 1 atm of pressure. So we can plug those in for those variables, but they give you grams of HCl? Well, nowhere in the ideal gas equation do you have a place to put grams, but you know what you have to do. What you have to do is convert to moles of HCl and then use that and plug it into the ideal gas equation. So you would say 49.8 grams of HCl, use the molar mass to convert to moles, and that gives you 1.3659 moles of HCl. Then you use that number and plug that in to your equation. 1.3659 moles of HCl times 0.082057 times the temperature. The temperature is 273 Kelvin because it's at standard temperature and pressure. And then you divide all that by the standard pressure, which is 1 atm. And if you multiply and divide all that out, you get 30.6 liters. All right, let's move on. So the next problem I want to do deals with what we went over in class. So the ideal gas equation is really useful when we're trying to relate different conditions of the same gas. We did this in class when I talked about P1 V1 equals P2 V2 when we were doing Boyle's law, where you can do the same thing for the entire ideal gas equation. So basically, the only thing that would remain constant would be the R, the gas constant. So we would write something like P1 V1 over N1 T1 is equal to the second condition, which is P2 V2 over N2 V2. It's the same gas, we're just relating two different conditions of that gas. Alright, and this problem deals with that. Let's try it. A gas initially at 4 liters, 1.2 atm, and 66 degrees Celsius undergoes a change so that its final volume and temperature are 1.7 liters and 42 degrees Celsius. I wrote ant, but that should be end. Anyway, what is its final pressure? Assume the number of moles remain unchanged. So of course, I set up all of my information, and I know that the volume 1, V1, would be 4 liters. The P1, pressure 1, is 1.2 atm. And then the T1 is 66 degrees Celsius, but of course I got to change that to Kelvin. So that's going to be 339.15 Kelvin. And then what they're looking for is the final pressure. So we need to find P2. But I know V2. They give it to me, it's 1.7 liter, and I also know T2, which is 42 degrees Celsius, but convert that to 315.15 Kelvin. So again, we're relating two different conditions of the same gas, so we would use the ideal gas equation, but we would use it twice, basically. So we would have P1 V1 over T1, because we don't need to worry about R, because R is a gas constant, and we don't need to worry about the moles, because they tell you, assume the number of moles remain unchanged. So that becomes a constant as well, so you leave it out, because it's the same in both states, in both conditions. So you would have P1 V1 over T1 is equal to P2 V2 over T2, but you have to solve for P2, pressure, the second pressure. So you would put everybody on the other side and leave pressure 2, P2 by itself. That ends up looking like T2 times P1 times V1 over volume, second volume times the first temperature, T1. And then if you plug everybody in, then it's simple. You just get your answer, and that answer happens to be 2.6 atm. So a good way to check your answer is make sure that all of your units cancel out. And of course they do in this case, but that's a good way that I could trick you, is giving you something that should not cancel out. So that would be a red flag, basically. But these type of problems should be very easy. They're simple plug and chug problems. Alright, so the next topic I want to talk about is density. We can do density calculations with gases as well. So let's talk about that. If we rearrange the ideal gas equation, we can calculate the density of a gas. For the density, we know that we have to have mass per volume. But we don't have mass in the ideal gas equation until now. I am about to rock your world. Alright, so we know the ideal gas equation as PV equals nRT. N actually comes from two other units. We get N by dividing mass into molar mass. So N actually equals to M divided by big squirrely M. You can see this on page 190 of your book, but little m is grams, mass, divided by big squirrely m, which is molar mass, grams per mole. So when you take grams and divide it by grams per mole, that bottom fraction flips and you end up canceling the grams and you end up with moles. So that's where moles comes from for the ideal gas equation. With that knowledge, we can use it to calculate density of gases. So all you would do is start from the main equation, PV equals nRT. Now we know that N actually is made up of little m, which is mass, divided by big squarely M, which is molar mass. So we take PV equals little m times RT divided by big squarely M. To get density, we have to get mass per volume. So we just isolate little m divided by V. So we put that on one side, and everything that's left on the other side is basically pressure times molar mass, that big squirrely M, divided by ideal gas constant times temperature. With this new information, we can also find the molar masses of gases, because that big squirrely M is molar mass. So if we were to ever ask you, can you find the molar mass of such and such gas? Well, all you would have to do is know that N is equal to little m divided by big M, and then isolate that big squirrely M, which is molar mass. Alright, let's try a problem. It says, what is the density in grams per liter of uranium hexafluoride, UF6, at 779 millimeters of mercury and 62 degrees Celsius? We start out with the main equation, PV equals nRT, but then we substitute what N really is made up of. So it'd be PV equals little m times RT divided by big squirrely M, which is molar mass. We isolate M over V, because that's density, that's what they want, and then we basically plug and chug everything on the other side and solve for it. So they give us the pressure, but in the wrong unit, so we have to convert it to ATMs. 1.025 ATM times the molar mass, which is 352 for UF6. If you don't know how to get this, you're in trouble. But it would be 352 grams per mole divided by the ideal gas constant in units of liter, ATM, mole K, times the temperature. They give you the temperature but in the wrong unit, so you have to convert it to Kelvin. So it's 335.15 Kelvin. You multiply and divide all that out, and you see that you get 13.1 grams per liter. You should notice that every unit cancels out except grams per liter, mass per volume, which is exactly what you need. And when we talk about the density of gases, we usually give it in grams per liter, because the mass that they occupy is really small compared to the volume. So grams per liter. Alright, so that's it for this video. I want to try to finish chapter 5 in the next video. It's going to talk about gas stoichiometry and Dalton's law of partial pressures, and then we should be ready for chapter 6. Alright, see you later.